Hello there. In this video we're going to introduce the beta function, which is a special function that is typically defined as an integral, and it has a very close relationship to the gamma function. So in this video we're going to introduce the beta function, and we're going to introduce an alternative integral representation for it, and we're also going to prove the intimate relationship between the beta and the gamma function, and then use that relationship to evaluate the beta function at a particular value. Alright, so as usual, we're going to begin by stating the definition of the beta function, and then work through another representation of the beta function from that can be a little bit useful at certain scenarios. So the beta function evaluated xy, so it's going to be a multivariable function of two, let's say, real variables. This is going to be defined to be equal to the integral from 0 to 1 of t to the power x minus 1, 1 minus t to the power y minus 1 dt. So if you remember the gamma function, so remember gamma of x is defined to be equal to the integral from 0 to infinity of t to the power of x minus 1 e to the minus t dt. So one may be able to make the observation that both of them have t to the x minus 1s. They do have different bounds, so if we can possibly represent the beta function as an integral from 0 to infinity, we might be able to justify a more deeper connection between these two functions. Because if, for example, the inputs of beta, x and y, are say like rational numbers, then you're going to have probably some trig substitutions that you would have to work out, which sometimes is a little bit tricky and sometimes not possible via elementary functions. So what I'm going to start by doing is getting another representation for the beta function that is a little bit more similar to the gamma function, and that may be a little bit more useful in developing another representation for beta. Right? So we're going to be starting with this definition. So we're going to start with beta is equal to the integral from 0 to 1 of t to the power x minus 1, 1 minus t to the power of y minus 1 dt. And we're going to be letting t be equal to 1 over 1 plus s. So this is going to be a u substitution, as most people will call it. So if t is equal to 1 over 1 plus s, then we clearly see that 1 plus s is going to be equal to 1 over t, which means that s is going to be equal to 1 over t minus 1. So when I perform this u substitution, as t goes to 0 from the right-hand side, this term is going to go to positive infinity. Minus 1 is still positive infinity, so that's going to give us an infinity term. And as t goes to 1, this is going to go to 1 over 1 minus 1, which is going to be 0. So that's going to give us an integral in the form 0 to infinity, which is probably what we want here. So let's see here. So if this is our definition for t, let us differentiate that. So that's going to give us dt is going to be equal to negative 1 divided by 1 plus s the quantity squared ds. Right? So that's the replacement for the differential t in terms of the differential of s term. So let's just replace that and let's work out the details and see what that actually comes out to. See if it comes out to actually anything nice. So that means the beta function xy is going to be equal to, so 0 is going to turn to infinity and 1 is going to turn into 0, so this is going to be the integral from infinity to 0 of 1 over 1 plus s to the power of x minus 1. And then for the second term, we're going to have 1 minus 1 over 1 plus s to the power of y minus 1. The differential of t is going to be equal to minus the differential of s, all divided by 1 plus s, the quantity squared. So we have a lot of 1 plus s's going on here, so it's possible we can sort of group them all in the same term since they're all in the denominator. So that's what we're going to do. And also notice that we have this negative hanging out, so we can revert these limits into a more traditional fashion, in particular the integral from 0 to infinity. So that's what we're going to do. So we're going to have the integral from 0 to infinity. I'm going to use our properties of exponents here. Nothing very fancy, so we have 1 plus x to the power of x minus 1. So we have some unlike fractions here, so I'm just going to multiply top and bottom by 1 plus s here. So I'm going to have 1 plus s minus 1, which is going to give us a positive s on the numerator, all divided by 1 plus s, all raised to the power of y minus 1. So I'm just going to distribute that exponent out into that term. So that's going to give us s to the power of y minus 1, all over 1 plus s to the y minus 1. And then over here, what do we have? So we have the differential of s, all divided by 1 plus s, the quantity squared. So we have 1 plus s to the x minus 1 times 1 plus s to the y minus 1 times 1 plus s to the 2. So that 2, that minus 1 is sort of going to cancel each other out, just leaving us with x plus y on the denominator. So we have that beta, x plus y, is also equal to the integral from 0 to infinity of s to the power y plus 1 all over 1 plus s to the power of x plus y ds. Right? And you can, of course, replace s with t if it makes you feel any better, because s is just a dummy random variable. So we're actually going to use this representation because since it's really close to the gamma integral, we can actually use this to derive a very, very important identity that connects the two. All right, so let's go back to the gamma function and let's sort of play with that definition and let's sort of bring that into the picture here. So remember that gamma of x is equal to the integral from 0 to infinity of t to the x minus 1 e to the minus t dt. So we have to bring into another variable y into this picture somehow. So we need to introduce a variable that ranges, say, from 0 to infinity. And then we're going to sort of manipulate it into a multivariable function just from a single variable function by doing another integral somehow. So to do that, what we can do is we can just replace t with another variable with respect to another variable and another variable that we're going to be holding constant. So we can let, for example, t be equal to cs, where c is just a positive real number. So c is going to belong to the interval 0 to infinity. You can include 0, it doesn't really matter, because it's actually going to serve as a bound for our integrals. As we know, it doesn't really matter if 0 is included there or not, at least from the Riemann integral perspective. So if t is equal to cs, where c is just a constant, that means dt is going to be equal to c times the differential of s. Right? And we can easily replace that here and here. And since t is a positive number, it's still going to go to infinity and also go to 0. So we have another representation for gamma in terms of this new variable c. So gamma of x is going to be equal to the integral from 0 to infinity. And we're going to have cs to the power of x minus 1 e to the minus cs times c ds. So we can distribute this x minus 1 to the c and also the s. So we have x minus 1 c's, but we also have this c hanging out over here. And since they're not dependent on the variable s, which is what the integral integrates over, we can factor out that outside of the integral to get the following representation. So gamma of x is going to be equal to c to the power of x times the integral from 0 to infinity of s to the power x minus 1 e to the minus cs ds. And again, this variable s doesn't really have any importance, so we're just going to switch back to t since we're not really going to use s anymore. So another representation for gamma of x is actually just going to be equal to c to the power of x, the integral from 0 to infinity of t to the power x minus 1 e to the minus ct dt, where c is a real number, more so on the interval 0 to infinity. Right? So that's another equivalent representation for the gamma function. Now, as I mentioned before, this is still of a single variable x, and I want to introduce another variable y so I can somehow relate that to the beta function. So I'm going to try and mirror what I have over here, just in terms of y, and instead of this t being the base, I'm going to let that integral be based on the variable c. So what I'm going to do is I'm going to multiply both sides by the term c to the power y minus 1 e to the minus c. So that's going to be on the left. And this is going to be equal to cx times c to the y minus 1 e to the minus c times the integral from 0 to infinity tx minus 1 e to the minus ct. That should be a t. Why is that a d? dt. So since c is assumed to be a positive real number, I'm just going to integrate both sides of this equation from 0 to infinity. So I'm going to sum all possible values of c for which this can be. So that's going to give us the gamma of x is going to be equal to the integral from 0 to infinity c to the power y minus 1 e to the minus c dc. So clearly this integral is independent of x. That's why I can sort of leave that gamma of x term on the outside function. And on the right-hand side, we're going to have two integrals. We're going to have an integral with respect to t and also an integral with respect to c. So we're going to have the integral from 0 to infinity, integral from 0 to infinity. They're the same bounds, so it doesn't really matter the order of which I'm going to find, at least not quite yet. And then we're going to have c to the y minus 1, e to the minus c. That's that term we introduced. We also have the c to the x term. I'm going to sort of hang him right there. Then we have t to the x minus 1, then e to the minus ct. Then we're going to have dc dt. So let's just look at this integral a little bit more intimately. So that has c, that has c, that has c, that has c, but this term here, this t to the x minus 1, is the only thing that does not have c. So if I take the integral with respect to c first, I can actually withdraw this out of this interior integral, and I'm going to have something a little bit more nicer. Also notice what I have here. This is actually the definition of the gamma function just evaluated at y, since c is just a dummy random variable. So I'm just going to replace that with its actual definition. So this is actually just equal to gamma of x times the gamma of y. That's going to be equal to the integral from 0 to infinity. So that's going to be our t integral, t to the power of x minus y, and then the integral from 0 to infinity. And then what do we have going on here? So we have c to the y minus 1, c to the x, so I can combine them. So that's going to be c to the power of x plus y minus 1. Then we have these two exponential terms. So e to the minus, so both of them have c, so I'm just going to factor that out. So it's going to be t plus 1, and then dc is our interior integral, followed by dt. Now again, notice that this integral here is similar to the gamma function, right? It's sort of like gamma of x plus y, except we have this annoying little t plus 1 term. So we need to somehow perform a u substitution in order to get rid of this. So let's do that right quick. So what can we do to sort of transform that into an integral? Well, notice that this exponent here, the c to the x plus y minus 1, has no dependence, at least in terms of the exponent, in terms of c or t. So I can actually just define this term to be equal to u, and then I'm going to have something to some power e to the minus u du, and then I can transform that into a gamma function. At least that's the idea, right? So what we're going to do is we're going to let u be equal to c times t minus 1. That's going to give us a minus u term. So that means c is going to be equal to u divided by t plus 1. All right, so we're going to replace that right where that c is. So what do we have? So if we differentiate, so we're going to have the differential of u is going to be equal to t plus 1 times the differential of c. Notice we're treating t as a constant here because we're on this interior integral here. We're not integrating with respect to t yet. That t variable actually is only variable with respect to the exterior integral, which we're not quite working with yet, working with anything yet. So we can still keep that t a constant as far as the first integral is concerned. Right? So once we have that, we're going to have dc is going to be equal to du divided by t plus 1. And now we can turn this integral into something that is a little bit more easier to work with. So what do we get? So we're going to have gamma x, gamma y is going to be equal to the integral from 0 to infinity of t to the x minus 1. Then we have our new integral here, so the integral from 0 to infinity. So you should be able to see that those bounds should not change. So we're going to have u to the power of x plus y minus 1, right? So that's the top. Then we're going to have t plus 1 to the power of x plus y minus 1. Then we have e to the minus u, and then we have our differential of c, which is going to be the differential of u divided by t plus 1. And then we have our differential of t just hanging out on the outside. So what do we got? So we have this t plus 1, x plus y minus 1. We also have a t plus 1. So that minus 1 term can sort of disappear. And again, this denominator here is actually independent of u, so we can withdraw that out to our exterior integral. So we have gamma x, gamma y is going to be equal to, so we have the integral from 0 to infinity. So we're going to have t to the power of x minus 1 all over t plus 1 to the power of x plus y. And then we have our integral to deal with here, so the integral from 0 to infinity of u to the power of x plus y minus 1 e to the minus u du, and this integral should appear to be a gamma function evaluated at x plus y. So we have gamma x, gamma y is equal to, so this is a gamma x plus y, it has nothing to do with t, So this is a constant that can be withdrawn outside of this exterior derivative, which is actually, exterior integral, which is the only integral that we actually have here. So this is just the gamma of x plus y times the integral from 0 to infinity of t to the power of x minus 1, t plus 1, x plus y, dt. And I'm just going to divide both sides by gamma x plus y. So I'm going to have the integral from 0 to infinity of t to the x minus 1, t plus 1, x plus y dt is equal to gamma x, gamma y, gamma x plus y. So what exactly is this integral that I have on the left-hand side? Well, that is precisely the beta function evaluated at yx, right? So therefore we have that beta yx is equal to gamma x, gamma y, all over gamma x plus y, but we know we can actually interchange these terms since multiplication and addition is commutative, so actually this is precisely beta of x, y. So this gives us the beautiful identity beta x plus y is equal to gamma x, gamma y over gamma x plus y. Alright, so let's just do a couple examples just to illustrate how we can use this awesome identity to evaluate some beta functions at some values. So let's assume we want to find, say, the integral from 0 to 1 of x to the power of 7 times 1 minus x to the power of, let's do 9. So it's 9 dx. So you should be able to see that this is precisely the definition of beta evaluated at 8, 10. So since that is the case, we can actually just use any representations for beta or identities that we have. So we already know that this is going to be gamma 8, gamma 10, all over gamma 8 plus 10, which is going to be gamma of 18. Since each of these values are natural numbers, we can actually just use the factorial representation for gamma, since these are all natural numbers and not fractions or anything like that. So this is going to be 7 factorial times 9 factorial, all over 17, the quantity factorial. And you can find that that's going to be actually a very small fraction, 1 over 194,480. So that's the value of this particular integral. But if these values, these exponents on x and 1 minus x are not integers, then you get a couple of interesting representations, right? So consider the following integral, for example, the integral from 0 to 1 of the square root of x times 1 minus x dx. So again, you should be able to realize that this is a beta function, at least it looks like one. In particular, this is the integral from 0 to 1 of x to the power of 1/2 times 1 minus x to the power of 1/2 dx, which is precisely beta of 3/2, because remember it's something minus 1, something minus 1. So if we use the gamma function, this is going to be equal to gamma 3/2, all over gamma 3/2 plus 3/2 is 6/2, right? So this is just precisely equal to gamma 3/2 squared, all over gamma of 3, right? So what is gamma of 3/2? So if you remember some of our properties of gamma 3/2, we have that recursion identity that is similar to the factorial. In particular, gamma of 3/2 is going to be equal to 1/2 times gamma of 1/2. And we still need to square that. The bottom is just 2 factorial, so that's not going to be tricky. That's just 2. So what is this? So we have 1/2 squared, so that's going to be 1/4. So we have 1/4. We have this 1 over 2 hanging out. And we also have gamma of 1/2, the quantity squared. So as we all know, 1/4 times 1/2 is going to be 1/8, and the gamma of 1/2 is actually going to be the square root of pi. And that comes just from a Gaussian integral. That's not a big deal. And the square root of pi squared is just pi. So that means this is going to be equal to pi over 8. Right, very beautiful simplistic value. Right, so that's the integral from 0 to 1 of the square root of x times 1 minus x dx. Right, so that's just a basic introduction to the beta function and its connection to the gamma function as well. and the very important identity that sort of relates the two. In particular, beta of x plus y equals gamma x, gamma y over gamma x plus y. Hope you enjoyed. As always, if you enjoyed, please like this video, consider leaving a comment, and if you enjoy the channel content, please subscribe. We publish several new topics every single week. Thank you.